Understanding the Schrödinger's equation is a very complicated process. As students, we lack the understanding of the mathematical modeling of particles. So, we are only expected to understand some basic ideas of this equation. It is impossible to comprehend this equation or quantum mechanics without an in-depth knowledge of mathematics. So, we just try to discuss the basic aspects of the Schrödinger equation. Before that, first understand the difference between classical mechanics and quantum mechanics. 1. Classical mechanics deals with macroscopic particles, whereas quantum mechanics deals with microscopic particles. Means classic mechanics deals with objects which we can physically touch, but quantum mechanics deals with atomic level. 2. Classical mechanics is based on Newton's laws of motion. Quantum mechanics takes into account Heisenberg's uncertainty principle and a Broglie concept of dual nature of matter. 3. Class mechanics is deterministic, whereas quantum mechanics is probabilistic. Deterministics means the results are exact, but in quantum mechanics the results are only probabilities. For example, let's imagine you are asking your girlfriend, "Will you have dinner with me tonight?" If her answer is yes, the result is deterministics, but if she answers like, "The probability for that is very low," means there is very low chance for that to happen. Likewise in quantum mechanics, the results also probability. In classical mechanics, Newton's second law, F equals ma, is used to find what path or position a given physical system will take over time, following a set of known initial conditions. For example, if an external force is applied on the object which is at rest, it will move from its location. Using Newton's second law, we can determine that object's position and velocity at a specific time. But in quantum mechanics, where everything is at atomic level, Newton's second law is not valid. There comes Schrödinger equation. In quantum mechanics, the analog of Newton's law is Schrödinger's equation, means wave functions of quantum objects are predictable using Schrödinger's equation. The equation is named after Erwin Schrödinger, who postulated the equation in 1925 and published it in 1926, forming the basis for the work that resulted in his Nobel Prize in Physics in 1933. The Schrödinger equation is a linear partial differential equation that describes the wave function of a quantum system. Before going further, now rewind. What is partial differential equation? It's a differential equation with many independent variables, means it contains many variables like x, y, or anything in a single equation. Now, you can ask a question. What if an equation contains only one independent variable? An equation with only one variable comes under ordinary differential equation. I hope you got the difference. Now coming back to the Schrödinger equation. In quantum mechanics, the fundamental concept is wave function. Wave function helps to find the electron's state. Schrödinger stated that only the probability of the location of an electron can be calculated. The exact location of the electron was not definite. Let's take an electron is orbiting the nucleus. If we apply some external energy, or photon, it will jump to higher energy orbital. From Schrödinger equation, we can find the position of electron. Thus, the probability of finding the electrons in the region of the orbitals is very high. An orbital is a wave function describing the state of a single electron in an atom. Schrödinger equation is given by H Hamiltonian operator E, wave function, I imaginary number, reduced Planck's constant, due by t, partial differentiation symbol. Now, let's see about this one by one. H Hamiltonian operator. An operator is a symbol for certain mathematical procedure which transforms one function into another function. So basically it means that we are operating on an expression and changing it to another expression. An operator has no meaning unless some quantity is put into it. For example, square root by itself has no meaning. When a value is put in, only then it gets its significance. In quantum mechanics, physical properties of classical mechanics like energy, time, linear momentum, angular momentum, etc. are expressed by operators. Hamiltonian operator is an operator corresponding with the total energy of the system. It is associated with the kinetic and potential energies at the subatomic level. Now let's see about wave function. Let's see very simple example. Imagine at the first day of college or school, you met a guy named Xavier. Definitely you have no idea about him, but when time passes you would get an idea about the behaviors of Xavier. After your observation about him, a wave function will be generated in your brain about the behaviors of Xavier in different domains like studies, sports, etc. When anyone asks you about the studies of Xavier, your answer will be based on the wave function, that is data about Xavier under the domain studies. In the similar way, representative electrons are studied and data are collected to form the wave function. Electrons have more degree of freedoms, means more domains. For each domain, a wave function is generated. Every electron have its own wave function. I hope you understand what is wave function. Just as we use Newton's equations to represent what happens to a ball when kicked, we use Schrodinger's equation to understand the behavior of atomic particles. Thanks for watching. For more videos, subscribe to our channel.